So Laplace equation uxx plus uyy equal to 0. I want to show that it satisfies something called the mean value theorem, which says that, let's say you have a solution satisfying this and it's defined on a circle, then the average value of this function over this disk is same as the value at the center. That's mean value theorem. Okay. Now, to actually produce this proof, you have to start with the Green's theorem. And there's the curl version and the divergence version, right? We need the divergence version. And what it says is that if you have the if you have some vector field, right, then the flux around a domain D, so if you have a domain D, and the flux, so you have some vector field F, then the total amount of flux of the vector field over this domain is calculated by taking F dot n, n is the outward normal vector, and you add them up going around the boundary, which gives you whether the vector is escaping or going in or going out. Right? The dot product is positive if the angle is less than 90 degrees. It's negative if it's more than 90 degrees, right? So if you have a vector that's escaping, then the normal vector, this is outward normal, so this is a unit outward normal vector, so their angles will be less than 90 degrees, which will give you positive contribution here, right? And then if you have a vector that's going in, then with the outward normal, it will have an angle more than 90 degrees, so it will give you negative. Okay? And the reason you do a dot product with the unit vector is that if you have any vector dotted with u, where u is a unit vector, that's called a component of that vector in the direction of u. Have you seen this formula? Sometimes people call this the scalar projection. Yeah. If you write this down in sine cosines, then it's really v norm times cosine theta, which is really the projection formula, right? If you have a vector and you're projecting it to another line. So what this is doing, you're projecting all the vectors as the normal component and you're adding them. And if this value is positive, you know that there's more vector components going out than going in. If this value is negative, then there's more things going in or out. That's called the flux. Right? And I spent some time trying to explain that the flux, the density of the flux, which is like you take the flux and divide it by its area, and you send the area to 0, you get what? That's divergence. Okay, so I sketched the proof of that. And what it means is that if you take the divergence of F, this is like a flux at a point. So inside this domain, at each point, you either have vectors spreading out from it or going in. So if you add them up all over the domain, then they're the same. Because one side is the density of the flux. Okay. It's a beautiful theorem, and yeah, it's a pity that most people don't finish multivariable calculus fully understanding what this means, because if you understand it, it just everything is so clear and easy. But we're going to use this, okay? So if you didn't get what I was saying, then please spend some time watching the videos on the relationship between flux and divergence. Those are on my channel. All right. What we are going to do is we're going to use the following fact, that gradient of u is what? What's a gradient? You take u and differentiate by x, u and differentiate by y, and just make a vector out of it, right? That's called the gradient of u. And here nabla is what we call, it's a vector of operators. Nabla is a vector of operators where if you do a scalar multiplication with this to this, then this gets multiplied to you to create this gets multiplied to this to create that. Okay, so this is our operator nabla. And if you do nabla dot of nabla u, what do you get? You get dot product between these two things, so that dot product is component-wise multiplication and you add, right? So you get the usual Laplacian, and we write down Laplacian as triangle that's like that, right? So people sometimes write nabla squared as triangle of u. And what we're going to do is, notice that this is a vector field, right? At each x comma y, this is a function of x and y, this is a function of x and y. You feed in x and y, you get a vector, right? That's called a vector field. If you have a vector field, what's a vector field? It takes in two values and it gives you back two values. That's a vector field, right? Or if it's a 3D vector field, then it takes in three values and gives you back three values. That's a three-dimensional vector field. So since this is a vector field, you can replace this one and this one on the right side. Oh, I forgot to say, this one here is what's called the divergence. So this Green's theorem, in our case, when you stick in the gradient of u into f, you get the following identity. And this is the form that we're going to use. U gradient of u dotted with n vector ds is equal to double integral of Laplacian of u dA. Okay. So let's write down the mean value theorem for the Laplace equation. If u satisfies above, then for a disk of radius r centered at a comma b, so I should say disk D, capital D, the integral of u going around this boundary and dividing by 2 pi r is equal to u at a comma b. And also, if you do a double integral u dA in the entire disk and you divide it by pi r squared, that's again equal to uab. Now before we prove this, I just want you to agree that the second one should follow from the first one. What does this mean? This means that you have the disk, a perfect circle centered at a comma b, and you're taking all the values at the boundary, you're adding them up, and you're dividing by its size. What is that? That's called the average, right? You add up every value on there and you divide it by its size. You learned in Calculus 1 and Calculus 2 that the average value of a function is defined as 1 over b minus a to b of f of x dx. What does this do? It adds up all the values of f over this interval a to b, and you divide by the size of the interval. You get the average. Same idea. So the average value of the function over this circle is same as the middle value. But then what does this do? That's like you're taking averages over the entire thing, but if the average of this circle is same as this, average of this circle is same as this, average of this circle is same as this, then since it's same for all of the circles, if you integrate over the entire circle, even the inside and take the average that way, you will get the same result, right? So do you agree that the first one should be implying the second? So we just have to show the first one. Is that okay? All right. So let's try to show the first one. Okay, and at some point we'll be making use of the Green's theorem in the special format that we wrote. Okay. All right. So what we do is we first parameterize the circle. How is the circle parameterized? Well, it's like RT is equal to A plus T cosine, no, R cosine T, comma B plus R sine T. Because what's cosine T comma sine T? What does this give you?
Unit circle?
The unit circle, right? If you multiply by R, what happens? This increases by the radius R, right? And you're adding A and B, what happens? The center 0, 0 now moves to A, B. So that's the parameterization of the boundary of the circle. Okay. Now let's try to calculate this one here. So you first have to make sense of what ds means. ds is really, so in line integrals there are two types. There's the one with dr, and people often write this out without the arrow on top, but it's really r with an arrow on top, and ds, where s is the arc length, change of arc length, so ds is really dr, that's taking the scalar of it. So it's the magnitude of dr. Okay. So this is a vector, whereas this is a scalar. Okay. So you can see some line integrals that looks like f dot dr. This makes sense because these are two vectors, and this is a dot product between them. But if you have a function which is a scalar value, then you can multiply by ds. Okay. So a function you integrate with respect to ds. A vector field you integrate with respect to dr, okay? And it's this case, okay? So remember, that's what this is. And you can only integrate by parametrizing the boundary. So as we move around the boundary, you're really evaluating the u on this boundary, right? You agree? You're evaluating the function u at this boundary. But what is ds? Well, we don't know how to integrate by ds. We only know how to integrate by dt. So how do you integrate by dt? You divide by dt and multiply by dt. That's how we always integrate, right? Even for the case when we do f dot dr, do we know how to integrate by dr? No, we don't. So what do? We divide by dt and multiply by dt. That's how we always integrate. But then, because ds is dr absolute value, this thing really is, so first t goes from 0 to 2 pi to go all the way around the circle, right? And then you have u, a, plus r cosine t, b plus r. Let me just write this as rt. That's easier. Okay. Yeah. Well, I wrote it explicitly, but you can just write like that. ds dt would be what? It will be the absolute value of dr dt, right? So let's differentiate this by r. What do I get? You know how to differentiate, hopefully.
D.
Huh?
Differentiate by t.
No, we're differentiating. Yeah, no, come on. Something's not right. Oh, yeah. We're differentiating by t. Right. So what do I get? The norm of, what do you get if you differentiate this by t?
Negative sine.
Negative r sine t. And what about this one?
R
cosine.
R cosine t. Okay, how do you take the norm of a vector?
Square and sine.
Square, right? What's sine squared plus cosine squared?
1.
1. So you end up with what?
R square.
This, yeah, but there's a square root, right? So this thing here would be square root of r squared sine squared t plus cosine squared of t, which gives you just r. And that r is going to cancel this r. So you end up with 1 over 2 pi, 0 to 2 pi of u, a plus r cosine t, b plus r sine t, dt. Because that r canceled with this r in front. Okay. Now, because we don't know yet that this is the value at u, a, comma, b, let's think about this. See, a and b are fixed, okay? T we've integrated away, so this is a function of what? Function of r, right? A priori, it's a function of r. So we're going to call this phi of r. Of course, if what we are trying to prove is true, then this should be a constant, right? Yeah. It wouldn't depend on r because we're saying that it's always same as u, a, comma, b. In fact, if we can prove that this is constant, then what is phi of 0? Phi of 0 would be you plug in 0 into r, right? And just you have u, a, comma, b, which doesn't depend on t at all. And you integrate by t, plug in 0 to 2 pi, but divide by 2 pi, so you just get u of a, comma, b. So the moment we define like this, we will see that phi of 0 is indeed same as u, a, comma, b. Right? So all it remains for us is to show that phi prime of r is 0. How's that? Makes sense, right? Okay, so let's do that. Phi prime, we're differentiating with respect to r. Well, look, u is a function of x and y, but x and y are both functions of r and t, but since we've integrated away the t, this integral right now will only depend on, well, this will depend on r like that one. Right? So if you differentiate this thing in here by r, if you do the partial derivative with respect to r, what happens? This would be, so du dr would be u differentiated by x times dr, dx dr. Is that right? Plus, what's the other one? That's this way. What's this other one? Uy. Dy dr. Right? That's just the multivariable chain rule. Right? Actually, I should be using partial here. But it's okay. So, what I have is 1 over 2 pi, 0 to 2 pi. I have, and then I want to rewrite this as the dot product between ux, uy, dotted with dx, dr, comma, dy, dr. Dot product. So if I use that, this left side is, what is this called again? Ux, uy is a vector. What's that called? Gradient of u. Okay? So this is the gradient of u. What's dx, dr? See, x is this, right? This is x, that's y, right? If you differentiate x by r, what do you get?
Cosine t.
And if you differentiate y by r, what do you get?
Sine t.
Sine t. Huh. But wait, what is this? This is exactly on a circle. At t, the outward normal vector would be exactly this vector. See, on the unit circle, this vector is same as this vector, right? So this is the outward unit vector. So now what you have is that this is going to be same as right? Okay. And then we use the Green's theorem as a double integral. And now this requires a slight interpretation of what it means because now the domain is this. So you may have to go back to the original idea where this now becomes ds, but then it's the same thing. You end up integrating back again over here. But what is this if it satisfies the Laplacian? Laplacian is equal to 0. So this is 0. So it's done. That's proved. Okay, so there are some important consequences. Sorry I'm going over time today. Let me just briefly say the important consequences. So number one, U is smooth inside the boundary because look at the graph of something. Can it have a jump discontinuity? No, if you have a jump discontinuity, you can't have the fact that at every point is the average of the nearby values. That's not true for places that, I mean, it might be true in 1D. No, that's not even true. If you have a jump discontinuity, this point has to be the average of this, but that's not true if you have a jump discontinuity, right? What's true is that if you have a straight line, then any average is same as the middle value, right? So in 2D, what that means, it always looks like a saddle. We talked about that before, right? If you have a saddle, then it's always true that at every circle, if you take the average value, it's same as the middle value. So you get a smooth value. And this is true even if you solve the Laplace equation with a discontinuous boundary. So we had an example where it was 1 here and then 0 here, and we solved it on the disk, right? The solution inside is very smooth, even if it has a discontinuity outside. Okay? That's a feature of the Laplacian. Number two, max-min can only happen at the boundary. Because, let's say you solve the Laplace equation outside. If the maximum happens inside, it doesn't make sense because average of this circle has to be the same as this one, but if this is higher than all the values in here, the average will be less. So there's no way you can have a maximum or minimum inside the domain. Okay? Another way to state this is that if the function obtains its maximum or minimum inside the domain, then it has to be a constant. That's another way to say it. Okay? So that's a direct consequence of the mean value here. And lastly, this will tell you the uniqueness of solutions. So if you have two u and v satisfying the same boundary condition, say 1 and 0 like here, then the difference between v minus u would have boundary condition what? The same value at the endpoint, so if you subtract, you will have the boundary condition to be 0 everywhere, right? But then, because of the maximum modulus principle, max-min property. If there's a non-zero value inside, what happens? It will either be positive, in which case it will be higher than the endpoint, the boundary, or negative, in which case it will be lower than the boundary. So it violates the number 2, the max min. So the only choice that v minus u would be is that it has to be 0 for entire inside. Okay? And that basically says that the solution must be unique. So these are the consequences.